start the recording, and I think we're good to go. And the floor is yours.
Great. Thank you a lot for the introduction. Yes, I will talk today about bridging knowledge graphs and system models for self-adaptive digital twins. And I will actually mostly talk about system models and self-adaptation in digital twins. So I'm going to use knowledge graphs not so much for modeling today, but for connecting different system models. So let's start with what problems in digital twins do I plan to address? Just as a quick reminder, what do we have as a digital twin? Well, we have a physical asset, we have some models around it or some kind of digital infrastructure, and there is data and commands going between them. However, the problem that I'm addressing is that while this works in a simple setup, reality is that the asset, right, the physical twin is already a very complex system, and the digital infrastructure and the models is also a complex system. And these two systems must be synchronized with each other. Indeed, if I remember correctly, the IEEE definition of a digital twin is a physical and a virtual entity which are synchronized with each other, right? And we are going to synchronize structure. Does the structure of my digital infrastructure match the structure of the physical twin? Do I have the right models? Do I have the right services? Do I have the requirements? And this is especially important as we evolve, right? So we cannot just establish that we have the correct structure now. My physical twin will change, but also the digital part will change, right? I will get new requirements. I will get software updates. I will have model updates. And I need to make sure that all of these happens in sync, right? So what we want to do is that we want to support engineers that while the digital twin evolves, they should not deal with every single update. There should be an automatic or an autonomous system that automatically resynchronizes your digital twin with the physical asset. And this, of course, needs to be encoded, right? So what does it mean to be synchronized? What does it mean to be consistent? What do I mean when I say my digital infrastructure is consistent with the requirements and physical assets? So there's some kind of domain knowledge that must be considered both during design of the systems, but also during its operations. And we are going to look now at exactly this domain knowledge, especially where do I get all these models that we need for this? And in this sense, we are going, if you think about what definition of digital twins we are using, more towards the 5D model, right? So a digital twin is not just model-driven control. It actually contains, obviously, the physical entities, it contains the virtual models, but it also contains services that operate on top. And while they are part of the digital infrastructure, they're distinct from the virtual models, right? A service is not a model. A service is something that builds on models. And then there is, of course, the data aspect, right? So both digital and physical entities produce a lot of data that needs to be analyzed, that we can learn from or like update our models with. So this sense, a digital twin this is what we consider the physical asset, and then we have the digital infrastructure here. And we care about these connections here between the entity and the model, but also between the entity and the service and the virtual models. I will not talk that much about data per se. And in this perspective, the physical asset becomes, well, obviously the asset itself, but also interfaces and connectors to the rest of the system. It's the control services that we offer, right? How do I control this kind of system? And from the data perspective, we have like the asset data, right? It can be an AS, it can be any kind of asset description that tells me what kind of machine is this, what are its capabilities, sorry, and what kind of standards does it adhere to. And it also has historical data. So what have I measured in the last time that I can see, for example, like when was I misstained? What is the sensor data that I get live? Sorry. The digital infrastructure is more involved, right? I have the design data, I have the simulation models, I have metadata about how did I design this, what's the provenance of my models. And I have a lot of services. Services that drive the simulation, services that drive the analysis, services that actually connect to these control services to control the asset, and data services that provide me maybe some kind of dashboard where somebody from business intelligence can look at and tell, well, this is not supposed to be doing what is operating right now. So a digital twin is always containing models, and these models are almost always multi-purpose. And the reason they're multi-purpose is because we have several services building on top of them. And this is a little bit of an uncommon view, or at least it was an uncommon view, to have a multi-purpose model. Because people often say, well, a model is an abstraction of something for a specific purpose. But in digital twins, you always have several purposes. I will use the same simulation model to drive the control, for example, but I will also use it to make more long-term predictions for predictive maintenance, for example. It will be the same model, and it must be designed in a way that is fit for both purposes. And in this view here, right, it becomes more explicit that the consistency challenge is there, right? Just making sure that the services have the right models to run on is already a challenge, right? My models change. Maybe I lose capabilities. Maybe I get compatibilities. Maybe I will have more services to run and I need to change a model, right? And this is all consistency. Is my digital infrastructure consistent in itself? And is it the right infrastructure for the asset? And digital twins, in this sense, are like very much in what's happening in engineering anyway, right? We have this idea about digitalization. And the situation right now is that we have a lot of people who produce a lot of documents who end up in a lot of paper, and smart people sit down and produce like an even bigger document that connects all the designs, all the decisions, all the requirements, all the laws that needs to be adhered to. So digital engineering is exactly what we need for digital twins. We need that all of this is digital, right? It must be a systems engineering problem that we have models from the beginning that we can operate on. We must have models to connect them with each other. And at the very minimum, it should be digital, right? I must at least say, this is the document I have been using, and I can access the document. So where do we get these models, right? So systems engineering is what gives us this model, right? They produce, for example, structural models, but they also give us the simulation models that we need. And these models are not just there for us, they're also there for what we call, or like many people call the digital thread, right? It's the whole history of the digital twin or of the asset in terms of its design. When did I change the model, right? So what model versions did I use? And all of this can be accessed afterwards to be used afterwards by the services that I have, right? Because maybe there are models that I used during design, which I only later realize needs to be updated and be added to a live digital twin, right? If you consider you have a simulation model in the beginning of your design, and then you refine it, and then finally you load it into the digital twin, and later you realize, well, I actually need the course model as well because it's a lot more performant. How do you express this, right? You need to say, well, I need a consistent infrastructure where this service has like ability to go for this model, which has like this coarseness, this level of abstraction, but also it must be up to date what I'm doing. It must not be up to date with the old state. But at least we have a chance to get the models, right? So systems engineering will deliver us the models and we will connect them into a graph. And the nice thing is that this will hold through all the system phases, so design, operation, and maintenance. And we don't even need to do this specifically for engineering. So the trend we have now is that we have digital twins of organizations, we have digital twin of the environment. If you think about it, a European digital twin of the ocean. And they use very similar techniques to like not model engineering, but also like ecological spaces, right? Where I have a model about how do sharks behave like in this part of their life cycle. Well, as they get older, I need to consider them differently. And of course, they have life cycles for the digital infrastructure that they're doing. And if you look at the platforms that have been developed in the last years in the European projects around biodiversity monitoring, they very much resemble service-oriented architectures that need to that have a connection with systems engineering. Because systems engineering is what you need to design the IoT that does the observation and connects it to a digital landscape. Okay. So what's a system model, right? System model roughly for me is a system a structure diagram, but it contains more things, right? It contains at least the asset structure, but it also links to the requirements and all the other elements needed during design and operations and decommissioning if you want to do decommissioning. And what do I mean by that, right? So we have things like what's the configuration? If you have a robotic arm or a camera, it's like what camera is it? What are its capabilities? What simulations did I run to design it this way? How did I design it this way? Who signed it off? Which standards do I confirm to? If something fails, what will be my failure models, for example? It also links to condition data, which may not be it describes the current state of the asset, and probably it links to it, right? So the system model does not contain the time series of what the sensor reads, but it contains an endpoint description where I can access it, right? So it contains a link to the digital part, which I can use live. And then you have all these other things, right? What are my operation and environmental data, right? So what is the data sheet, for example? And then what's the business side of it? So why did I design the system in the first place? What value framework drove these decisions, and so on. And then you should add up at something like this, where you go from requirements to an asset together with a digital twin and a digital thread. And now we have all these models, right? So we have our nice systems engineering world. People produce our structure models. The structure model tells us exactly what the system looks like, why it looks this way, and where it connects to the digital part, right? So where can I get live data? And from this perspective, coming back to the very beginning, digital twins are often seen as behavioral self-adaptive systems. So my model adapts the behavior of the physical system. And even if there's unforeseen circumstances, I can still adapt it. And behavioral self-adaptation is, for example, if I have a robot and it bumps into a wall that is not there in its world model, it will automatically plan how to get around the wall. But we are interested in structure, right? And before I come to structure, I just want to very quickly introduce MAPE-K. So MAPE-K is a framework for self-adaptation, and that splits the system into two parts. There's the managing subsystem and the managed system. The managed system, in this perspective with digital twins, is just our physical asset. The digital system has at least four components. You monitor what's going on. If something happens that you do not think is right, you analyze what is wrong, and then you make a plan what you should do to get into a nice state, and then you execute it. In the robot example, you see a wall that shouldn't be there. You analyze that it's not there, but right of it seems to be of opening. The planner will tell you, turn right, go a bit, turn left, and go straight through the opening. And the executor is the robot who will actually take this plan and then drive around it. And we want to do this now for structure. And we were going to do this in a declarative way. As said, our aim is to develop an autonomous systems that helps us with data management and model management, right? I don't want that every time something changes in my knowledge about the system, somebody has to go down and change my digital infrastructure. So we are going to do this in a way that's suited for automation. And in the following, I will use a small example of a greenhouse. And the greenhouse is monitoring plants. And we are going to assume that for each point in the life cycle of a plant, I need a slightly different analyzer. In terms of the digital twin, I need to exchange this component whenever I see that my physical system is in a different state. And let's say I have two possibilities for my plant that I'm analyzing, right? So either it's healthy or it's sick. And it can go from sick to healthy and back. But let's say if it's sick, then it needs to be watered a little bit less because it's kind of plant that's like prone to overwatering. You could design this, no problem. You could say, well, if I go along this transition, just replace this component. You can do this in a very operational way. But what if we have complex life cycles? What if we have a second life cycle about like small plants, medium-sized plants, and big plants? Again, maybe all of them need different analyzers, and I could do it for each of the transitions. And you can imagine it becomes a mess if you combine this, right? So I can have a healthy small plant, then it becomes sick, but then it's also a medium plant. And I get like all these transitions in between. And for each of the transitions, I need to pre-plan about how to replace a component. And this is just a very simple model of one plant. Imagine you have like a huge factory where you have to exchange digital components all the time just by monitoring whether you're in a maintenance cycle or not. You don't want to do this manually. What we want to describe is what does it mean to be consistent with this stage and how do I get there? Sorry. Yes, that's what I said. So what we do in terms of architecture is that we put a second layer of self-adaptation on top. We do the same thing. We have a managing and a managed system, but the managed system is the self-adaptive system of layer 1. So we do not only monitor what's the physical twin is doing, we also monitor what is our digital infrastructure, our monitors, analyzers, planners, and executors in this case. And we monitor the relation between them. And if we see that the relation is off, then we see, well, what exactly is off? For example, oh, I'm in the wrong state. I need to exchange an analyzer. I plan which configuration, how to change my configuration, and then execute it. And executes for us means change the level 1 managing system by exchanging digital components. For example, changing an analyzer. And if you're out of MapK, this would be like start new services or like shut down services because we cannot guarantee a certain service level. And we're going to do this in 2 ways. For each lifecycle stage, we are going to define when is an asset to be considered in the stage, right? So when is an asset, when is a plant sick? When is a plant big? And then we are going to say, when is it consistent? If I have a sick plant, what are my requirements on the digital architecture? And then self-adaptation becomes generic because I will just say, is this plant sick and big? It's sick and big. What services must be running if it is sick and big, and what services must be shut down if it's sick and big. And then I can just add and remove them without explicitly modeling all the transitions explicitly. So let's look at an example on how this works before we come to like knowledge graphs. So formally, I promise you there will be not more complicated formulas than this. Formally, we have our stage, and the stage is defined with respect to an asset class like flowers, plants, robots, and C are the kind of components we look at. And for our example with MapK, this will be level 1 monitors, level 1 analyzers, level 1 planners, and level 1 executors. Member just tells you which are the plants that I look at, so what does it mean to be sick, and consistent tells me under which conditions on the digital infrastructure do I consider this consistent. As an example, this is my definition of sick life cycles. I say that I consider something sick if the NDVI sensor returns a value lower than 0.5, where NDVI, I, to be honest, forgot what exactly it stands for, is a sensor that essentially measures how much chlorophyll is there in the plants. And we say for this species, if you drop below 0.5, we consider you sick. And we say we are consistent if for each member of this class, so for each sick plant, we find an analyzer which makes sure that the moisture is below 5, whatever 5 means in terms of unit, right? So it must exist somewhere. There can be more, but at least this one must exist, right? So this is a requirement on our digital infrastructure. If we have a plant of this way, this is the physical twin, the digital twin, we must find this analyzer service. And then a life cycle. A life cycle is a set of these declarative stages such that each asset that you have is always in exactly one of the stages, right? I cannot have a sick and a healthy plant. Of course, if you want to avoid like xeno behavior and this kind of stuff, you can introduce a small class in between where you say you're consistent with both of them, but you're a member of this intermediate class. So if I want to have a life cycle, this very first life cycle of healthy and sick plants, I have a membership predicate for health, which is just the opposite of it, right? So together will always be healthy or sick, and the analyzer now keeps the level under 10 instead of under 5. So we can water more if we're healthy. And you can compose them, right? So if I give you 2 life cycles, all you need to do is to check, are they compatible? Which means that if I have an asset which is member of both stages, is there theoretically a way to be consistent with both of them, right? So if I'm small and sick, is there any way to configure the digital twin to make sure that I'm consistent with both these requirements? If 2 life cycles or 2 stages are compatible, this just means I can run them in parallel. I don't need to like build this explicit transition model where I have exponential blowup. I will actually skip over this a little bit. Yes, and how does self-adaptation now work? It's very simple. You look for each asset, for each life cycle. What are my assigned components, right? So which components are responsible for me? You check, am I a member of one declarative stage and am I not consistent with it, right? If I'm consistent with it, then analysis tells you you're perfectly fine, just continue doing whatever you're doing. And then you use abduction, right? And abduction means under the assumption that I am consistent, give me a logical theory that explains it. So I know that I'm not consistent. I know I have the wrong components, but I give you a complete description of my infrastructure and I ask you, but if I want to be consistent, give me an explanation for it. This explanation would tell me, well, if I remove the analyzer, which is like below 10, and replace it with one below 5, then you would be consistent. So you're almost there, right? You just get a plan now, which tells you, well, remove everything that's not there anymore in your explanation and add everything that has been added for it. And in the paper, it is like a little bit of extra overhead if you have multiple life cycles. So here's an example. Let's say we run our self-adaptation loop like once in a while, and now we discover, well, for this plant P, the NDVI is 0.4, so it's a member of SIG. We also know that it has exactly one component assigned, which is this analyzer below 10. So a moment ago, it was still healthy. So we know it's not consistent. And now we ask, well, give me a list of predicates of this form that would explain that I am consistent. And it would tell me, well, if I have this analyzer, if you remove the old one, I add the new one, and I end up in this state. So I'm now a member of the SIG class, and I'm consistent with it. So this is very nice, no? The problem is a little bit, this is a nice architecture and a nice framework, I think, to work in. Problem is a little bit, how do I implement it? Where do I get all these logical predicates from? And how do I do this weird abduction thing and all the other operations? So what we need to do is we need to be able to reason over data. Especially we must be able to deduct membership and we must be able to do abduction. So we must be able to explain. We must be able to represent structured data. So we must have a format which we can put our system models in, right? Because remember, the system model describes me, there is a plant and these are its stages and this is the infrastructure connected to it. And we must be able to actually query over it. And to no little surprise, the solution is knowledge graph. I will not give a full introduction into knowledge graphs, but I quickly want to go over how it looks like. And everything I have told you has been implemented when I was still in Oslo at the University of Oslo in Einar Wochjanssen's group on the greenhouse DT, which is a small little system where so this is an NDVI sensor, measures whether this basil is healthy or not, and depending on what changes, indeed, the water pump. So it's not visible right now, but you can automatically water the basils. And this is implemented in the small language. So everything I have told you is an architectural view, but we have actually tried it out. And you can download all this and try it out yourself. Yes, so we have system models, we put them into knowledge graphs. They are capable of all these operations. I will show an example in a little bit. We need to put more into them, right? We also need to put the models into them, which are not structure, which are behavior. And the nice thing, and this is the reason we developed small, is that you can just put functional mockup units into it. And indeed, you can, if you reuse the architecture for other languages, just put any kind of asset model into it. You can put an AAS into it, and it just ends up in the knowledge graph. So if I have a simple behavioral model, and this is a monitor, and all it does is it takes two FMUs, the system and the shadow, and it checks whether the values are close enough, right? So it just does 1 second steps at each time and checks what's the difference between them. And if it's like above a certain threshold, it throws an error. And you can just put it into the graph as well. And you can run a query of, I always have two different models loaded, right? I don't have the mistake where the system and the shadow model are the same. So everything ends up in the graph. So we do structural self-adaptation, which means that the physical system and its system models end up as part of the knowledge graph. And the digital twin infrastructure also does that, right? So I have a full graph data description of these are the services that are running, these are the monitor components that I have. These are the mapk loops that I'm running right now, which means that consistency and repair, so these queries that I run on them, are indeed queries. They are queries over a knowledge graph. So they're independent of what exactly is my digital twins. If I change my digital twin, like for example, I go to a different programming language or a slightly different framework, I can most likely just reuse the same queries because I do not go into the deep details of this is Java or like this is C sharp, sorry. So let's have a small example, which is not a plant because it was a bit difficult to do this for plants, but for smart houses. And what we want to do is that it's a composable house, right? So it can be extended. It's a modular small building. If I add a room, I want to automatically detect there is a room and start a new service for it. And if I remove a room, I should automatically shut down the services that happen for it. And this is the only graph query that I will show you, and I will slowly go through it. What we do is we ask, go into the knowledge graph, which contains both the digital infrastructure and the system model, and ask it, are there rooms for which I do not have the digital services running? This is how it works. This line says, so everything which is asset colon is describing the asset, and everything with program colon is describing the digital infrastructure, because it's a program. What this one says is, give me all the rooms in the physical twin, give me all the walls left and right for them, and give me the room ID. So after executing this part of the query, I have all the rooms and the ready room. This query here inside the filter says, give me all the rooms which are part of the program, so all the digital twins that are running, and then remove all those which have the same ID for one asset. So what you will get afterwards is a list of all the rooms for which you did not find a single digital twin, which are exactly the rooms you just added. And I will also get the walls left and right for it, which means after running this query, I will have the analysis result. Oh, I found a room. You don't have services running for it. By the way, it's left of this wall, so I know exactly where to load it. And the repair function afterwards is create a new room, put it left or right of the wall that you have found, and then start all the other services you need. And we have done this for small systems in Oslo with the greenhouse. We have done this together with Aarhus University for this robotic arms, where we have more interesting things than just rooms or plants. So we will make sure that we actually load the right controllers for this robotic arms. And if I would have changes in the services, I could automatically react it. This was done together with Santiago Gil, and we have like a very nice architecture, right? If you look at the architecture, you don't need to go into details. We have here the physical part with the two robotic arms, and we have here a simulation unit with the functional mockup units. And you need to make sure that you actually load the right FMU for the right robotic arm, because they, if I remember correctly, have the same interfaces. So it's very easy to switch them out. We are still working on integrating this into a service-oriented platform, also together with Aarhus. And the digital twin with the greenhouse can actually be downloaded. And it's a very nice system to experiment on with digital twins and self-adaptation, because it costs like 120 euro to build it yourself. And there are no fancy equipment requirement. So you can experiment with digital twins if you don't have access to like industrial scale factories. This is what it looks like. All the plants here are dead, but it's just because this is a picture from 2 years ago. But like this also includes like a complete software stack with InfluxDB and so on that you can just reuse. I want to show like one more example about what we did more recently and come back to the Oslofjord digital twin. There the situation is very similar. The physical twin for us is a bunch of fish which are swimming in the Oslofjord, I hope, and the IoT structure around them, right? So what we want to do is we want to support ecologists and biodiversity experts in managing the hypothesis and data. So of course we cannot always react if there's a new fish, but we can react if there's a new data source. So if a new data source gets out, I want to know which scientist do I have to notify that something has happened. So how do I have this relevance? And this is for us also a consistency question, right? The digital twin for us are models, simulation models about how do fish, for example, look like, but also like wave behavior. We have the data which comes from the cameras, and domain knowledge about what's a fish and what kind of fish do we have in the Oslo fjord. And of course, we don't have a full loop. We just get insights into it. We can say things like, oh, you have the hypothesis that in the Oslo fjord there's a lot of cod, but actually after looking at all the data, I have not found a single one. Yes, and one reason you need is like you don't get new cameras randomly in the Oslo fjord, but you don't get every time a live stream. You can also get historical data. So somebody comes back with their boat and they have recorded data. You get in retrospect have new videos to analyze. And analyze in our sense is now computer vision, right? So I have a video and I need to find out automatically like which fish did I observe, which kind of species do you have? So again, does the assumptions I have about what fish are there consistent with what I have modeled in my digital infrastructure? This is an interface that we have for the Oslo fjord. So here, Oslo is up here in case you wonder. I can select this square and say, I think that this is a good place for cod, and then I will get digital infrastructure for that, meaning I will automatically generate monitors that say, well, a cod needs degrees under 15-degree temperature and desalinity. Give me all the data in this square and run my runtime monitoring on it. And if I see a cod, if it's over 15 degrees, then I will get an alarm that says, well, you have this hypothesis that cod only lives here under 15 degrees, but look, it's like 18 degrees water temperature and I still see cod. And now I could like get more sensors. I could get new observations. I said like either from long-term observations or even data citizen science will like make photos of fish. This is one of our cameras, which is exactly here at the nearest point. This is me lowering one of the cameras to observe more fish. And this is set up and it works, right? So I can say this is now not cod, it's Bergknapp. If I add new data, it would automatically analyze what kind of computer vision system to set up, and then set it up and automatically send me a message saying, well, we have observed something that is confirming your hypothesis or going against it with exactly the same kind of declarative lifestyle modeling that we also used for the industrial systems before. And that's it. I just want to show a small example because I have 2 minutes left. I hope you can see this. This is the system model of the Oslo Fjord digital twin. This is not SysML, this is IMF, but it's the same idea. We have a system breakdown, and we model both the structure and the requirements and the functions. So we have the blue parts are the physical systems, and this color are the functions. So we have the Oslo Fjord digital twin, and it's there to collect and store environmental data, which is expressed with this arrow. And for example, what we have here is that we have camera installations at certain locations. And why is the camera there? Well, to record video, because we want to have video observations, because we measure something. Similarly for the drifters, which are like cameras or other sensors you could throw into the water. But we also have a model of the digital infrastructure. So here we have each data set explicitly represented. And you can go down deeper into the model and you see more data for the data set, like where is it from, what does it cover, what data schema does it belong to. Which means that I would add a new data set to this model, and then I would rerun the self-adaptation. And the first thing that you would do to run it is that you would build now. And the first thing that you would do is that you would regenerate the knowledge graph, and you can ignore the error messages. They're just that I don't find the logger. And so this would take all the system models and combine them into a knowledge graph, and then afterwards run queries to find out is it consistent or not. And if you wait for a second, I will be able to show you the knowledge graph. Sorry. But this one takes a while because there's like actually quite a big system model in the background. And we link it with some ontologies already. Yes, so here you see we add some axioms that were not there before, and if I now looked at this knowledge graph, I can see I can identify that some nodes are identical to each other, and this is like full RDF that I can run normal graph queries over and find out whether it's consistent or not. So yes, what have I talked about? Have talked about how do we get help with managing structure of digital infrastructure of digital twins. And in particular, we looked at where do we get the models from, and the answer is we get them from systems engineering, right? Because they need to do their work anyway to digitalize the engineering workflows, and we can just reuse it then to ask what does it mean to be consistent? What is the structure I am supposed to be consistent about? I have not talked in detail about knowledge graphs, but I hope you believe me that they are the foundation to actually link all the system models together in a way that I can ask this very generic, am I consistent questions without knowing too much about the modeling language. And what I mainly talked about is this two-layered self-adaptation structure where I reuse map K and have two of them in a hierarchy, one which is adapting towards structure, and the internal one is, let's say, classical digital twin, which is self-adaptation with respect to behavior. And that's it. Thank you.
All right. Yeah, thank you. Thank you very much, Eduard, for your interesting presentation on the adaptation aspects of digital twins. I'm now stopping the recording, and